Section 3.5 we started last time. We were looking at algorithms. We specifically looked at our exponents and their properties. And we did a couple of examples with those. And what we're ready to start this time is actual algorithms for multiplication. So the first algorithm we're going to do for multiplication is the one you know and love, called the standard algorithm. And you take, whoops, from last class it's still on. You take 48. We'll do our regular standard one over here, and then I'll show you the expanded one. Yeah, because I don't actually have this one written down in the notes. Okay, so if we take 48 times 32, somebody walk me through what you're going to do.
Do 2 times 8.
2 times 8, which is 16. So I write down a 6 and I carry the 1. So I've got that weird carrying thing going on that we talked about with addition already. What do I do next? 2 times 4. Well, that's weird because now I'm taking a 1's digit and I'm multiplying it by a 10's digit. And after I do that, what am I going to do?
Add the 1 on top.
I'm going to add in the middle of multiplying. Do you guys see that sounds a little bit weird? I'm supposed to be multiplying. Now I'm adding in the middle of it. Okay? So you're telling me I get a 9 there. Now what?
An x below the 6.
I put a 0 or an x or something in this spot right here, and that seems a little bit like magic. Okay, I'm just going to put something in there.
Wait, how do you get a 9? I'm sorry.
4 times 2 plus 1. Right? Multiplying, we're multiplying. This is a product. Okay? All right, so we put the magic 0 down for no real good reason. I mean, like, nobody really tells me why I do that. We're just going to do it, right? Yeah. Then what are we going to do? We're going to do 8 times 3, and we're going to get 24. So I'm going to write down my 4. And I hope when I carry my 2, I write it on top of the 1. Otherwise, now I've got 2 numbers up there, which would be loads of fun, right? And then what?
4 times 30 is 12 plus 2 would be 14.
Yeah, so there I go adding in the middle of my multiplying again. And then when I'm all said and done, I get to add again, right? Okay, what do you get?
1,536.
Oops. All right, so that's the standard algorithm. It's very efficient. Takes up very little space, truly, comparatively to some other things. But it's not very intuitive. You've got multiplication and addition happening in the same middle of the problem. You've got a 0 that you're locating in the middle here, which students forget. And if they forget it, now they've got a value that's much smaller than they should have, right? So we've got a lot going on in that standard algorithm. So let me show you what the expanded algorithm looks like. We did expanded algorithm in the last section for addition and subtraction. And what we did is we separated the 2-digit numbers into their 2 single-digit values with zeros. So like 48 is written as 40 plus 8, and 32 is written as 30 plus 2. Okay? And what we do is we multiply just like this to get you the 16 here, and we just write a 16 down. And then we multiply the 2 times the 40 to get 80, and we write down 80. Okay, and then we're going to do the same thing with the 30. We're going to do 30 times 8, so we're going to get 240. And then we're going to do 30 times 40 so that we get 1,200. There's no mysterious zeros, and there's no addition in the middle of my multiplication. I do end up with 4 values to add up in the end because it was a 2-digit by 2-digit number. If you did a 3-digit by 3-digit number, it'd be more, obviously. But most of the addition is pretty simple. A lot of zeros and stuff are there. So I have a 6 in the 1's column. 8 plus 1 plus 4 makes 13. So I'm going to write down my 3 and carry my 1. 1 plus 2 plus 2 is 5 for 1536. The beauty of this method is that it separates the addition from the multiplication, and I don't have any zeros that I have to explain where they came from. Now, I'm sort of poking fun at this 0. It comes from somewhere, but I don't think it's usually explained very well as to where it's coming from. Okay? So let me just explain where it is coming from so that if and when you do in fact teach with a standard algorithm, which you will at some point if you teach multiplication, you're going to use it. Let's talk about where this 0 comes from. Does anybody remember, or can you think about why there's a 0 there? But why? Ashley?
Because you're multiplying now by 30 and not by 3.
When I multiply here, in fact, it's the 3. When I multiply by the 3, I'm actually not multiplying by 3. I'm multiplying by 30. So the 0 there is coming from the fact that I'm multiplying by 30. I write down the 0 part of it, and then I kind of ignore it, and I multiply by 3 instead. That's where it's coming from. All right? Yes?
I learned to always put an X there. That's just what my teacher.
That's really interesting because I've never heard anybody say that before, Hannah. Yeah.
I've grown up doing that.
Has anybody ever seen that before either? To put an X there? Emily has? I have seen people leave it blank, just not put anything in that place as well. That's another thing I've seen. And it probably had to do with either how they learned it or how some textbook was representing it and they wanted to follow what the textbook was doing. It is really important when you're teaching that for the most part you do what your textbook does, because otherwise it's going to confuse students, and then it's going to confuse the parents too, because you're not following what they did. Or provide resources that explain what you're doing in form of worksheets or newsletters or something like that. All right, this next method is actually my favorite. This is called partial products. And I think this method's probably my favorite because I'm a very visual person, and I like the visualness of this. It really is a lot like what we just did with the expanded algorithm, but it gives a picture to what we're doing. So we're going to write the 40 and the 8 along the top, and we're going to write the 30 and the 2 along the side, and what we're going to do is we're going to draw a grid in between. So I've got this right here, and it's a grid that's a 2 by 2 grid because I'm multiplying 2 by 2 numbers. If I did a 3 by 2, I'd have a 3 by 2 grid. If I had a 3 by 3 number, I'd have a 3 by 3 grid. Okay, so the grid's just going to match my numbers. And then what I do is inside each box, I do the multiplication for the row and the column that I'm on. Okay, so does it matter? It does. It does matter because we're going to do something else later where we're going to do it on the right-hand side. So just for consistency, so that you don't have to remember which one matters, I'm going to always put them on the right-hand column. Yeah. All right, so we're going to multiply in this box, this column, the 40s column, and the 30s row. So what's 40 times 30 in this box? Close. 1,200 or 1,200, right. All right, in this box, I'm going to multiply 8 times 30, and I'm going to get 240. In this box, I'm going to multiply 40 times 2, and I'm going to get 80. And in my final box, I'm going to multiply 8 times 2, and I'm going to get 16. And then I'm going to add these values together, just like I did on the previous screen. You can do it in whatever order. I tend to go biggest to smallest. So 1,200, 240, 80, and 6. And of course, you add them together, you get the 1536 we had before. Okay? Yes?
16.
What was it?
For the last number.
Oh, thank you. I wrote it right, I just didn't copy it down over here. Right, thank you. Yes. Now, I want to show you what this is actually doing. This is an abbreviated picture of what's happening. But do you remember when we did in section 3.3 a model for multiplication called the area model? You guys remember that? Okay, and we did it as like 3 times 4 or something like that. They were smaller numbers. But what you really have here is you have a big old giant grid. And it's a 40 by 32 grid, so it's a little bit wider than it is long. And it's 48 wide. It looks something like this. This is the 40, and this is the 8. Okay? So I'm trying to give at least a little bit of depth perception to what's going on. Scale. The other one is supposed to be 32. Well, here's my 2. So this is the 30, and this is the 2. So what you actually have here, and it makes sense now, is there's 1,200 units in here, right? And down here in the little corner, this is 6 or 8 times 2, which is 16 units down here. It's really length times width. It's just written in an abbreviated way because I'm telling you what, if I want to multiply 48 times 32, I don't want to draw the visual picture that actually shows the dimensions of it every time. Does that make sense? But these two go hand in hand. There's an actual physical object named area that associates with what we're doing, and this is the partial products method. Okay, everybody good with that? So I like this one coming from a visual person. Now, I know I talk about my kids a lot, so occasionally I have students that get really irritated with me about that. But I talk about them because I know about their educational experience, and I think it's useful for you because you guys are teaching. I have an 11-year-old right now, and when she was in 3rd grade and they were learning to do multiplication with 2-digit numbers, the standard algorithm was really difficult for her for whatever reason. And she's not a dumb kid. She's very bright. She wasn't getting it. It wasn't clicking. And she's perfectly fine with the standard algorithm now, and that's what she uses, and it's no problem. But I showed her this one. She didn't like this one. She wasn't a fan. But she loved the next one. So we've seen lattice algorithm before, right? We did the lattice algorithm for addition. I'm going to show you a lattice algorithm for multiplication now. So we're going to do much like I did on partial products, except I don't write down 40 plus 8. I just write down the single digit. 4, 8, 3, and 2. And this actually does matter that the 3 and the 2 are on the right-hand side with what I'm about to write down. That's why I do the 30 and the 2 with the partial products on the right-hand side as well, just so that we don't have to remember where it matters and where it doesn't. You're going to draw that 2 by 2 grid. Do you remember what else we did with lattice? Yeah, we did these diagonals. That's what you're going to do next. You're going to cut the diagonals on each of your boxes. And in each of the boxes, much like with partial products, you're going to do the multiplication. So you can start with any box, doesn't matter. I tend to start with the top left box myself. So I do 4 times 3 and I get 12. Now, no matter what you do, you will get a number that is a 2-digit or a 1-digit number. What's the biggest 2 numbers, single-digit numbers you can multiply? 9 times 9, and that gives you 81. You're not going to get a 3-digit number, right? Okay, so you're definitely going to get a 2-digit or a 1-digit number, which means that the 2 corners of this box are all you need. This number is 12, so the 1 goes in the top left-hand corner and the 2 goes in the bottom right-hand corner. If I go to the right corner next, I have 8 times 3, which is 24. The 2 goes in the top left-hand corner. The 4 goes in the bottom right-hand corner. So now I'm going to go to my second row. 4 times 2 is, that's a single-digit 8, so the 8's going to go in this bottom corner. If it bothers you to not have something filled in, you could put a 0 there. It'd be okay. Or you can just write the 8 here. And then I have 8 times 2, which gives me 16. So the 1 will go in the top left-hand corner, and the 6 will go in the bottom right-hand corner. Okay, so that's all the multiplication that you do. Again, it has that very nice feel that both of the last 2 methods do, that we do all the multiplication first and all the addition second. We're not mixing the 2 up. The next thing that we do with this method is we extend, if you will, the diagonals. Some people like to continue extending them down, that's fine. Some people don't, they like to just go kind of around the box, that's fine too, but I'll draw them this way. We do have to start in the bottom right hand corner and add, this is a 6. Now, you do not add these values to it. The only thing you're adding are the numbers that are inside the box. Okay, so what I just highlighted into has nothing to do with the addition I'm doing. So I add the 6. The next one I add is 4 plus 1 plus 8, which is 13. I write down the 3, and I do have to carry the 1. So now I have that sort of 1 carried, plus the 2 and the 2 that are there, which gives me 5. And then I don't need to carry this time, and then I have the 1 in the top corner. So my solution is 1536, written down here on the bottom. Or I will tell you that some people don't like to write it like that. They might do this instead. And just curve it around, and then they've got this right here. So there's the 1536 curved around. I don't care which one you do. It doesn't matter. Okay? That's lattice. And for whatever reason, that's the one that my daughter thought made the most sense, and that's the one that she learned. And in using that frequently enough, she got the standard algorithm down, which is more efficient, and she started using that one more later. All right, division. There are only two models for division that we're going to do. All right. First one is the standard algorithm, which you guys know and love. So how do I do 623 divided by 5?
Put 623 in the box.
Mm-hmm.
5 on the outside.
Mhm.
You say like how many times is 5 going to 62? Which would be 12.
You usually do 6, right?
Okay.
So how many times does 5 go into 6? Once, and you put the 1 up here and you say 1 times 5 is
1.
5.
Sorry, I'm thinking the
You're already ahead of me, yeah. And then you subtract. So 6 minus 5 is 1. And then you bring down a 2, usually, just the next one digit that you need. And then you say, how many times does 5 go into 12? And you say 2. And 2 times 5 is 10. And then you subtract. 12 minus 10 is 2. And then you bring down a 3. How many 5s go into 23? 4. 4 times 5 is 20. And then I stop with 3 because I'm using whole numbers. I'm not doing decimals or anything right now, okay? So we would stop there and we would say that our answer is what? 124, and we usually use an R and then 3. Okay? Yeah.
The way that I was taught was to have the arrows to break down.
Oh,
Does
that's
that
fine.
matter?
Nope, you can do that. If it helps you to see the arrows pulling the number down. Totally cool. Yeah. Okay, so this is a standard algorithm. One of the things, and I don't think there's anything sort of innately wrong with the standard algorithm, but it does hinge on the fact that you knew your multiplication tables of 5s, right? I mean, you did need to know that in order to use that very well. And that's fine. You should know your multiplication tables in order to do division. However, I will tell you that for some children, learning disability kinds of stuff makes that part of it a very difficult task. The classroom that my daughter was in for 5th grade had students who they had learning disabilities that kept them, not just like they were lazy, didn't know how to do it. They had learning disabilities that kept them from getting those multiplication tables down. That's going to make division awfully difficult if you don't know your multiplication tables, right? Okay. So I'm going to show you another method that does not rely on you knowing your multiplication tables. And then we'll stop for today. This is called repeated subtraction algorithm. You kind of start the same way. You're doing the 620. And what you're going to do is you're going to subtract a number that is 5 times a power of 10.
Why are we starting with 620?
Oh, 623 is what I meant. Thank you.
I got scared. I said,
Sorry about that. 623. We're going to subtract 5 times the multiple of 10. So what do I mean by multiple of 10? Well, 1 is a multiple of 10. 10 is a multiple of 10. 100, 1,000, 10,000, so forth. We're going to do 500, right? So I can do 5 times 100. It's the biggest power of 10 I can multiply 5 by and subtract it. If I try to do anything any larger, it's too big. So I'm going to subtract off 500, and I'm going to end up with what? 123. Now, I'm not going to multiply 5 by 4 here. I know some of you want to, because 5 times 4 would be fantastic, right? But we're not going to do that. Or 5 times 5, or 5 times 6. We're not doing that. We're going to multiply 5 times the power of 10. What's the power of 10? 10. I can't multiply 5 times 100 and subtract it. It's too big. But I can subtract 5 times 10, which is 50. What do I get? 73. Okay. Can I do that again? Yeah, I can do 5 times 10 again. And that gives me 23. Sorry, I thought before we were at the 23 already in my mind. I was thinking 5 times 4. You wanted to subtract. No worries. All right, 23. Can I subtract 5 times 10 again? No, it's too big. But I can subtract 5 times 1, which would give me 18. Can I subtract 5 times 1 again? What would that give me? 13. Can I subtract 5 times 1 again? I can. That would give me 8. And if I do it one, it's a lot of steps. If I subtract it again one more time, I get 3, and then I'm done, right? I never subtract anything different than 5 followed by zeros. That's the nice part. The not so nice part, as you imagined and as you saw, is that you repeatedly subtracted the same thing over and over and over again, and that becomes annoying the more you do it. Let me show you how you get your answer. Your answer is these numbers all added together. That's 100 24, remainder 3.
Wait, where did we get the one? 24?
This is 100,
Okay.
this is 20,
Okay.
and that's 4. That's repeated subtraction. And we will pick up and finish the rest of this section next time. We are so close to done, and then we will be able to call it good for chapter 3.